And so, I leave it to you.
So thank you very much for inviting me. This talk might have been called Lambda Calculus and its theory of program approximation. But in fact, we will see two main approaches, one based on Böhm trees and the second one on Taylor expansion. Okay, this does not really work. Okay, so first I will show the big picture. We'll start recalling the lambda calculus, even if you're there, probably it's not your first time that you see the system. And the theory of program approximation was based either on denotational models, we'll see a little bit of Scott continuous semantics, or with a more syntactic, if you want, approach based on possibly infinite trees that represent a possibly infinite evaluation of a program. But then, as Lionel said, the linear logic entered the picture, and in particular the relational semantics of linear logic that will be the elephant in the room, in the sense that I'm not really going to talk about it because Delia will later, more or less, will present it as non-idempotent section types, and Guy McCasker will give a generalization, so you will see this as a particular instance. But the point of the relational semantics can be morally described by a syntax. So we'll see a resource calculus whose terms in a sense represent the point in this semantics. And then we'll see that indeed one can approximate a program computing its Böhm tree, but it can also compute its Taylor expansion, which is something that translates a term into a series of resource terms. And then we'll see that these two different approaches are actually related. So there is a tight link between Böhm trees and the approximation computed by the Taylor expansion. And we will see how this new approach based on Taylor expansion can be used to prove properties of the calculus itself. So this is the ambitious plan for this morning. We'll see how much I can actually say about it. So in the beginning, there was the untyped lambda calculus introduced by Church around 1932. And the idea is to represent a program not as a list of instructions, but rather as a function. So one has lambda terms that are either variables or lambda instructions or application. And in this context, the computation, a step of computation becomes a substitution. So lambda x m applied to n reduces to m, where all free occurrences of x are substituted by n. And we'll call a program a closed term, so a term without any free variable. So I guess everybody knows this. The point is I'm considering the pure untyped lambda calculus, no constants, no programming language constructs. So I will give some examples and introduce some notation. For me, I is the identity, lambda x dot x. Then I will call k the first projection, f the second projection. And then, since we are untyped, we can define the self-application, so the program delta that take an x and apply x to itself. And of course, if you apply delta to itself, what is going to happen is that delta takes the other delta and duplicates it, so it actually reduces to delta delta itself. And so we are introducing non-termination. So the theory of program approximation is needed if we want to handle complexity. We can write a program that is very big, hundreds of thousands of lines of code. And the question is how to approach a very complex code. And so the idea is that we would like to have a method to specify the meaning of the basic instructions of the program, and then something that is compositional, which means that the meaning of the whole program can be retrieved from the meaning of its basic components by application. So basically, you want that the interpretation of m applied to n can be computed straightforwardly from the interpretation of m and the interpretation of n. And so in the denotational semantic approach, the idea is to define a model as a more abstract mathematical object in which we interpret programs. And this allows us to abstract away from the technicalities of the syntax and prove properties of the program using mathematical tools that we all like. Another approach is to use a system of approximants that can be seen as the little bricks, elementary bricks that compose the whole program. And then the idea is to retrieve the whole program behavior by performing some kind of limit of all its finite approximants. So this can be done either denotationally or more syntactically. And the first model of lambda calculus, D infinity, was introduced by Scott in 1979. And later in 1977, Barndrecht proposed a more syntactic approach, in the sense that Barndrecht proposed to define the meaning of a program by defining the possibly infinite tree that represents its whole computation. So it is a model, but based on syntax. And the idea of Scott's denotational model is that one has a topology behind that. So the idea is that we consider data as part of sets with an order that intuitively says that D is smaller than D prime if D, seen as an argument, is less defined than D prime. So this means that the bottom is the least defined element, which can be understood as complete lack of generality. So given a CPO, so a complete partial ordering like this, one can define the Scott topology by specifying what Scott open is. So a set O is Scott open if it is upward closed, which means that whenever an element is inside, all the elements bigger than that one are also inside. And then for all directed subsets A, where directed means non-empty, downward closed, and closed under finite supremum. So for all direct set A, if the sup of the set A belongs to the open set, then the open set intersects this set A. So examples are the set of all elements of the A that are different from bottom. This is a Scott open. Or fix a D in the little d, the set of all elements that are not smaller than D. We'll see some examples later. And this topology is a T0 space, which means that all points that are different can be topologically distinguishable. There exists an open set that contains one but not the other one, or vice versa. So when we speak about Scott's continuity, we mean continuity with respect to this topology. And one can prove that a function f from D to D is Scott continuous if and only if it commutes with all directed supremum, with the supremum of all directed sets. Intuitively, being Scott continuous means that a finite portion of the output must be generated by a finite portion of the input. And that's why Scott decided to represent programs as a Scott continuous function, because he had this in mind. And this, in fact, allows us to handle recursion. So if you have a function, a Scott continuous function from D to D, one can always compute its least fixed point. So not only the least fixed point of f exists, but one can compute it as the sup of the application of f n times to the bottom element. So this gives a recipe to compute this least fixed point. You start from the bottom, you apply f once, and it gives a finite portion of the output, and then you apply f twice and gives another little portion of the output, and you take the limit and get the whole least fixed point. And this is used in the notational semantics to give meaning to recursive programs and definitions. Okay, so in lambda calculus, what does it mean to be the fixed point of a lambda term? X is a fixed point of a lambda term if m applied to x is equal modulo beta to x. And it is an open problem, by the way, whether it is true that every closed lambda term, every program, has either one or infinitely many fixed points. So, of course, if the program is constant, it has just the one fixed point. The identity, for instance, has the whole set lambda. And this is an old open problem. You should all try to close it. Right. And then, now that we know what a fixed point is, one can define fixed point combinators. So terms like this that satisfies ym beta equal to mym. Why? Because this means that for every m, ym is a fixed point of m. So it's a way of constructing a fixed point in lambda calculus. So if we want to define a model of lambda calculus, we need to understand what are all the possible behaviors of lambda terms. And the first behavior is the most simple one. You take your term, you start reducing it, and after a finite amount of steps, the computation stops with a completely defined term, a beta normal form. So these terms are called beta normalizable. And in some sense, the result is completely defined. Then we have seen terms like omega that never produce any output at all. But you can also have terms that do not reduce directly to themselves, but for instance, a p that reduces to p1, that reduces to p, but they never produce any stable portion of the output. And this is completely undefined. These are called unsolvable or meaningless terms. And then there is a notion in the middle. So you can have a program P that computes a first portion of the output, but together with this stable portion of the output, it gives also a subprogram P1, and then one starts computing P1, and it gives another stable portion of the output, but also a subprogram P2, and you can continue. And only if you push this computation to infinity, you get a completely defined but infinite program. So for instance, you can define a lambda term that gives the whole sequence of numbers of pi. So Barendrecht decided to exploit this idea to introduce a tree for representing the whole infinite computation of a program, possibly infinite. So the idea is that if a program is unsolvable, then it is completely undefined. And then we have seen in a CPO the complete undefinedness is represented with a constant bottom. So you say that the Böhm tree of an unsolvable term is just bottom. Otherwise, the term gives a stable portion of the output, this portion in blue. And one can prove that it always has this shape, so a bunch of lambda struction and then a variable that can either be free or one of the abstracted variables. And then k programs, M1, Mk, apply to the variable y. And so you take the arguments of y and you put them as subtrees. And then you keep computing the Böhm tree of these subtrees. So at first sight, if you look at this, it might look like an inductive definition, but it isn't, because here is not an equality, but it's a beta reduction. So during the reduction, the program can grow exponentially, actually. So each M1 here can have a size which is much bigger than the original program M. And so in fact, this definition is not really well defined. It wasn't in 77, but then later researchers said, well, but this is just an application of the co-inductive principle. So in fact, you can say you can see this as a formal definition, but it is not by induction, but rather by co-induction. And that's why it can give infinite trees. So for instance, if you compute the Böhm tree of a fixed point combinator, the one that I defined above, before, you start reducing, and it gives this lambda f dot f that is never going to change afterwards. So it is a stable portion of the output. You can put it in the beginning of your tree. And then you keep going, and this gives another f. You put it in the tree, another f. You put it in the tree, and you keep going. So this gives, as Böhm tree, lambda f dot f with the son f, which is a son f, and so forth. So in general, if you have a normal form, the Böhm tree of the normal form is basically the normal form itself. If you have any unsolvable term, well, by definition, this Böhm tree is going to be bottom. And then you can collect many results in infinite trees, like this one. So you can have a lambda xx with an occurrence of x here, and then you keep going like this. So you can do these infinite patterns. So now that this infinity comes to play, some weird things can happen. So a problem is, for instance, given two terms, how do you know that their Böhm tree is different? And it's not enough to check whether the terms contain different free variables, because what can happen is that a free variable is there, is never erased, but is pushed to infinity. It will never appear on the Böhm tree. So exercise, you define a term m that reduces to lambda zx dot x applied to mz. So you then apply this to a fresh variable y. And what happens is that the application of y gives lambda x dot x as a first portion of the tree, and then this mz becomes my, so the free variable y is still there, but it does not appear in the tree. So the Böhm tree of this is going to be an infinite tree of lambda xx. And so if we apply two distinct variables, we have two terms, my and mz, that are beta distinguished, because if you are beta equal, you cannot have two different free variables that are never erased, because being beta equal by confluence means you have a reduct in common, and so this reduct should contain both y and z. But the Böhm tree is the same. So as a little digression, now that we understand better co-induction, one can see the Böhm trees as the normal forms of an infinitary lambda calculus. So one can start from the grammar of lambda calculus, but rather than take the grammar inductively, you consider it co-inductively, which means that you can generate infinite terms that are not normal, and then you can define a rewriting on this, and if you add a constant bottom for representing your unsolvable terms, you can prove that this system is confluent and strongly normalizable, because you are allowed to do these infinite reduction sequences. And so what you can prove is that a Böhm tree is nothing else than the infinitary normal form of considering this beta bottom reduction of your finite lambda terms. Okay, but this was just an FYI. So these kind of approaches are very popular now, because with theorem provers like Koch, one can formalize this kind of proofs. For instance, recently Lukas Kzajka, sorry for my pronunciation, gave a new proof of confluence totally written in Koch of this reduction. Okay, so this was a little scary for people that are not well aware of the co-inductive principle. And if it's scary for you, imagine for the researchers at the end of the 70s, right? Where co-induction was not really very known and popular. So at the time, the idea was how to work with these Böhm trees whose definition we don't really grasp. Well, the idea is to look only at the finite trees and then find a way of putting them together. So we can slice an infinite tree into finite trees that are pieces of output that can be obtained in a finite amount of time. And then, of course, the bottom induces an ordering on this tree, because bottom is smaller than anything, in particular smaller than lambda f dot f applied to bottom, which is smaller than this one. So the idea is that if you replace bottom on a finite tree for something more defined, you get something bigger. So the Böhm trees are naturally ordered like this. So one can define what are these finite approximants of a tree, which has the same grammar as tree, but this time we take it inductively. So it's basically the grammar of lambda calculus normal forms, where you have an extra case that something can be bottom. So the ordering is the one generated by saying that bottom is smaller than any other approximant, and then the contextual closure. And one can describe the supremum between two compatible approximants as the following. So bottom sub A is equal to A. If you compute the sub of two terms, they must have the same shape. So either they are both applications or they are both lambda structure. And what you do is that you compute inductively the sub of each component. Okay, so if you give me a lambda term, how do I compute all its finite approximants? Well, the point is that I can define a notion of direct approximant of this term, which is very easy. If the term has a radix in head position, I say, well, this is bottom. I don't want to know what it does. Otherwise, it has a free variable in head position. And here I can say, OK, here I do recognize the finite portion of the output, the bunch of lambda x's and the y. And so I can compute the direct approximant of its arguments and 1mk. So this gives a direct approximant. It's direct because I don't need to do any computation. You give me the term, I apply the definition, and I give you the approximant back. But then, if I want the set of all finite approximants, I need to close it by beta reduction or beta equality. So basically, you give me the term, I apply the direct approximants, but then I reduce the term and keep applying it, and I collect all of this in a set. What is the idea? The idea is that if I perform one step of computation, the direct approximant can only increase, because one step can generate a portion of the output more, and so you get something that is more defined. So it's bigger in this ordering. And then by definition, you get that if two terms are beta convertible, then they must have the same set of approximants. And then this set is an ideal, so it's non-empty. Equivalently, the bottom is in the set because the bottom is an approximant of any term. It's downward closed, but here I cheated a little bit. I closed the set under downward, but one can also take a different definition and prove it. And then the difficult point is to prove that if two approximants are in the set, then also their supremum is. How do you do that? Well, take A1, A2 approximants of M, then by definition, there exist N1 and N2 that are beta convertible with M, and such that A1 is smaller than the direct approximant of N1, A2 is smaller than the direct approximant of N2. But now, what does it mean that two terms are beta convertible? By confluence, it means that there is a common reduct. And we have seen that the direct approximants of the term can only increase along reduction. So this omega n1 will be smaller than the direct approximant of R. And the direct approximant of n2 is smaller than the direct approximant of R. So we know that there exists a bigger element in the set that approximates, covers both. Okay, so the set of finite approximant of a term is an ideal. It does have a supremum. And what one can prove is that the Böhm tree intended as the infinite tree that we defined before can actually be computed as the supremum of all its finite approximants. So in fact, well, for bottom it's easy because it's just, for omega it's easy because it's just the singleton bottom, but for the Y combinator as before, we start from the bottom and then we keep going and apply the direct approximant, and then doing the sup is just creating all the portion, and the infinite supremum gives the whole infinite tree. And if you define this set of all finite approximants of M carefully, you get a one-to-one correspondence between finite, these sets of finite approximant of terms and Böhm trees. So the set of approximants is a different way of describing the Böhm tree of a term. But now, usually, if you can introduce, when you introduce a model of lambda calculus, so we can say that Böhm trees are models of lambda calculus. You introduce the interpretation. So here the BT is interpreting a lambda term as its Böhm tree. But so it also induces an equivalence on lambda terms. So we can define that M is BT equivalent to N if and only if M and N have the same Böhm tree. And then one wants to prove that this equality is not strange, which means that it is actually an equational theory of lambda calculus, which means that it does contain the beta equivalence and it's closed under context. So for all context C, if M has the same Böhm tree of N, then also C of M has the same Böhm tree of C of N. So the first part we already did with the finite approximants, but this part is difficult. More precisely, the difficult part is that if I give you a term M and a term N, and I even give you their Böhm trees, then if I ask you, what can you tell me about the Böhm tree of M applied to N? The answer is probably not much, because the Böhm tree of M can be an infinite tree, and then apply an infinite tree to another infinite tree, anything can happen. So this is the difficult problem that we need to handle. So I think one of the first proofs was applying the tree topology. So the set of Böhm trees can be seen as an algebraic CPO with this ordering that I described. So we can endow it with Scott topology. So for instance, the set of all terms that are solvable, you can prove it's an open set. Why? Well, because the complement is closed. So the singleton, not the singleton, the set of all unsolvable terms is closed. And then in this particular topology, the unsolvables are compactification points, which means that the only open set containing all unsolvable is the whole set lambda. And one can also prove that the normalizable terms are isolated points. So the set of all terms that are beta convertible with a normal form, a beta normal form, it is an open set. And then you need to prove that application and lambda abstractions on lambda are continuous, Scott continuous. And then you can prove that this equivalence induced by Böhm trees, it is actually compatible with application using the continuity. So you suppose that M has the same Böhm tree that N prime. You want to prove that m applied to n has the same Böhm tree as m applied to n prime, which is the difficult case of the context closure. So by contradiction, you assume that it is not the case. And then what you get is that since the Scott topology is T0, there is an open that does contain, say, m applied to n, but it does not contain m applied to n prime. But we have seen that the application is continuous. And so by continuity, there exists an open set U that contains n prime, but such that mx, where x is unsolvable, is in the set U, is contained in this open. And this is absurd because we said that if we started from the hypothesis that m has the same Böhm tree of n, and as not the same Böhm tree of n prime, and we found that m prime is in this, which is included in O, which is absurd. So this proof is not very easy to understand. The next one, this one, is much more understandable. You can use this infinitary lambda calculus to prove contextuality, because you just say, well, you assume that Böhm tree of m is equal to Böhm tree of m prime, and similarly, you assume that Böhm tree of n is equal to Böhm tree of n prime, and then you use the confluence of the system. So the system is strongly normalizable, so you can first compute the Böhm tree of m. In parallel, you compute the Böhm tree of n as the normal forms in the system, and the application is well defined between infinite trees. And now by confluence, this is the same thing as, it has a common reduct, the Böhm tree of m applied to n. But then if you assume that the Böhm tree of m is equal to the Böhm tree of m prime, and the one of n equal to the one of n prime, this part is equal to this one. So you can also normalize this part. You get something which, by the unicity of normal form, but must be the same thing as the other way. So this is much clearer, but you need to use co-induction, define the system, prove confluence. Is not an easy proof of this. Okay, and then, with these kind of techniques, you can also prove the genericity lemma, which states that if you have a lambda term m and an unsolvable u, and m applied to u gives beta normal form, then in fact m cannot really use the unsolvable to produce this normal form. In other words, it needs to erase u to produce n. But this means that for all lambda terms L, m applied to L is going to give the same result, n. So also here there is a topological proof. You start by saying, well, if you consider the beta equivalence class of the beta normal form n, it is a Scott open. Then by continuity, you get that this set is open and it contains all unsolvables. Why? Because, the beta equivalence is the leftmost strategy is normalizable, which means that this equality can be turned into a reduction by left outermost strategy. But this means for normal forms, being equal to a normal form is the same thing as having the same Böhm tree, because it is finite. But then this is closed under, it equates all unsolvable terms, which means that u can be replaced by v for all unsolvable V. So this set O must contain all the unsolvables. But we have seen that the only open set that includes all the unsolvable is the whole set lambda. And then this is true for all L in lambda. Okay, so this was the classic approach to program approximation. And now we are going to introduce the resource calculus, which is the, well, more recent approach to program approximation based on linear logic and differential linear logic. So the resource calculus I'm going to introduce is based on the following. So the lambda calculus is not resource conscious. What does it mean? It means that when you apply lambda xm to an argument n, this argument can be either erased if x does not appear in m, or duplicated if x has several occurrences of x in m, or copied an arbitrary amount of times. So this is not very resource sensitive. On the contrary, the idea of linear logic is to decompose the intuitionistic arrow, A arrow B, as a linear arrow from A to B, where you mark with a bang the resources in A as being duplicable or erasable. So this suggests that a step of beta reduction can be decomposed into more elementary steps. So the first idea can be, well, let's define the linear lambda calculus, in which every time you write lambda x dot m, you impose that m contains exactly one copy of x. You can do that, but it's not very interesting. I mean, there are some interesting problems, but only because since the system is so easy, then it makes sense to count the classes of beta normal linear lambda terms. And so it is interesting from a combinatorial point of view rather than a computational point of view. So the idea of the resource calculus is to have a linear lambda calculus, but in which variables can occur multiple times, but they cannot be erased nor duplicated during the reduction. So this was introduced by Erard and Regnier in the differential lambda calculus paper. And then, as it usual, someone else changed the syntax. And then the new syntax can be seen as coming from Gérard Boudol's paper, The Lambda Calculus with Multiplicity. And that's the syntax I'm going to use today. So in the resource calculus, there are three syntactic categories. You have terms that have the same grammar as lambda calculus, except for application, where T is not applied to another term U, but rather to a bag of terms. So a bag is just a finite multiset of terms. And the idea is that the resources in the bag are linear. They cannot be duplicated nor erased during reduction. And so the terms are the protagonists, the main characters of our calculus. The bags are the multiset of linear resources. And then for technical reasons, one needs to introduce sums. So the sums here are finite sums of terms. And the idea of a sum is that you have S plus T that morally is either S or T. But we never actually perform the choice because we want to keep our system confluent. So intuitively, you think about the sum as an inner choice operator, but you never reduce it in this sense. So we assume that the sum is associative and commutative. We can write sum like this. And the multisets, I'm going to present them as with a multiplicative notation, which means that 1 is the empty bag, the empty multiset, and B1 times B2 is actually the union, multiset union of B1 and B2. So now when we do definitions by induction, the case of multiset is 1, the base case. Otherwise, every bag can be split into a singleton bag, union, the rest of the bag. So sums are not really important from the point of view of the calculus, but they are useful if you want to actually give the definitions that work. So they are useful, but not very important. And so all constructors of this calculus are linear. What does it mean to be linear here? Well, it's basically the fact that you commute with the sums. So if you look at my grammar, I never allow to have a sum under a lambda abstraction. I never allow to have a sum under an application. But it will be convenient to write this kind of terms as syntactic sugar for the external sum of, for instance, lambda x dot ti here, and so forth. So basically, since all the constructors are linear, one can always extract the sum and put the sum to the surface. So a particular case of this is the 0 case. An empty sum is 0, but then this means that lambda x dot 0 is 0, t applied to the 0 sum of bags is also 0, 0 applied to a bag is 0, and a bag containing a 0 becomes 0. So basically, if you generate a 0 at a certain point in the term, it destroys the term because the sum goes out, and the term disappears in the sum, because 0 is the neutral element of the sum. So what's the idea of say, well, I have a lambda x dot t applied to a bag of 3 terms, S1, S2, and S3. Well, this means that I expect that in T there are exactly 3 occurrences of X. And so I can substitute each of these as I for exactly one occurrence of X in T. And I can actually count the amount of occurrences of X in T in a very easy way. So the problem is that, well, it's a multiset, so they are not ordered S1, S2, S3. How can I choose who takes the first occurrence, who takes the second one, who takes the third one? Well, but I do have the sum, the choice, right? So I consider all possible choices. So this is going to reduce to the sum of terms where each occurrences of X is replaced exactly once by one of the SI, and I consider all possible combinations. Okay, but this is the case where I have 3 elements in the bag, I have 3 occurrences of X. What happens if T only contains 2 occurrences of X? Well, I promised I would never erase or duplicate my resources. But I can self-destruct. So if there is a mismatch between the number of occurrences of X and the number of arguments, the whole program becomes 0. And so in fact one can define this formally by defining a linear substitution that is going to fetch each occurrence of x in t and substitute it by one element s. So the linear substitution of s for x in t is defined like this. So if it's applied to a variable y, there are two cases. If y it is the x that we were looking for, then this is just s, because we can substitute. If it is not, then we cannot do the substitution, and this becomes 0. On a lambda struction, it enters within the lambda struction. On an application, well, the occurrence that I'm looking for could be on T or could be on B. So I consider both cases. This makes the sum of the linear substitution of S for x in T plus this one. So it goes inductively within T or within B. But this means that I need also to define what does it mean to linear substitute something in a bag. And so by induction, the base case is the bag is empty. In this case, I didn't find any occurrence of x. It's going to be 0. If it is a singleton, well, this x must be inside. So I go within. And again, if I have an application with two non-empty bags, I just do the sum and look for x in B1 or in B2. And this can be used to define a baby step beta reduction. It is that lambda x dot t applied to a bag, non-empty bag. I can always extract one element from the bag and reduce to lambda x dot t, where one occurrence of x is substituted by s in t. And the rest of the resources remain in the bag. So notice here that we didn't erase the lambda x, because it still might get things from B. And B has decreased, the bag has decreased by 1. Eventually, it will be empty. When it is empty, then I can erase the lambda x and reduce, if there are no more occurrences of x, to t. If there are occurrences of x, this means that there was a mismatch between the occurrences in the bag and the occurrences in t. And I can destroy the term and goes to 0. So this is going to do a lot of small steps. But one can define a normal step semantics where you say, well, I take the whole bag and I directly do the actual substitution of each occurrence of x in T for S1, by S1 Sn, whenever the degree matches the number of S1 Sn. Otherwise, it's going to be 0. So you can extend these notions to sums by saying that, well, if you have a sum and one component reduces, then the whole sum reduces. And notice that sum can arise in the computation. So here, for instance, you have this baby step. You need 3 steps. What happened? Yeah. You need 3 steps just to consume this bag of resources. And then when if you start consuming this one, you have this B that can go to the left occurrence of y or the right occurrence of y. And then you generate this sum. And then you can continue till reaching the normal form. In the normal step semantics, you do this in exactly two reductions. So then Pagani and Tranquilli prove that this baby step and the normal step semantics are actually equivalent. It's easy to see that this calculus is strongly normalizing. Why? Because there is no duplication. So every time you contract a radix, there is, I'm speaking about the normal step semantics. Every time you contract a radix, you erase a lambda y, so the size of the terms decreases. So the only tricky point is that you need to define the size of a sum as the multiset of the size of the terms. And then you can prove that one step of reduction is making reduce this ordering. It's basically because there's no duplication and the size of each individual term decreases. And then you can prove confluence just by saying, well, this calculus is locally confluent. So if you do one step on one side and one step on the other side, you can always close. And then conclude by Newman's lemma that says that if a thermal writing system, it is confluent and it is strongly normalizable. Sorry, it is confluent if it is strongly normalizable and locally confluent. So the terms here can die of starvation if they are waiting for like 2 occurrences of x here and receiving just 1 bag of resources. They go to 0. Or surfeit. So if you're waiting for 1 occurrence of f and you get 1, you can go on and replace this f for h. But then I'm waiting for 1 occurrence of g. I get 2 things. I go to 0. And then this non-determinism it can arise from a computation. So it's basically hidden in the bags. When you reduce the bag, you can have a choice between occurrences, and a sum can appear from a single term. So summing up, we have this wonderful calculus, which is linear, but in which we can use several occurrences of variables. And whenever a radix reduces to a sum which is non-zero, this means that the t here must use each si exactly once in the reduction to the value. And on the contrary, if all terms goes to 0, so if the program t becomes the empty program 0, it means that there was a mismatch between the amount of arguments and the one expected. So this calculus is strongly normalizing, confluent, and linear. Nothing gets erased in a reduction to something that is not 0. Its expressive power is basically nothing. You cannot do sums, natural numbers. So we didn't really increase on that. So the question is, why did we do that? Well, is it really interesting? And the answer is yes, because this calculus is the target language of the Taylor expansion. So basically, this linear substitution of s for x for one copy of x in T can be seen as a derivative operator. the derivative of t in x in s. Okay, this derivative operator. So what we are trying to do is to have a differential theory of program approximation. So when in analysis, when you try to understand a function, what you can do is to compute the derivative and then study the derivative. And the derivative gives information on the function itself, because it explains how the function varies when its argument changes, right? And then one can express the function as an infinite power series of linear functions via the Taylor expansion. So the brilliant idea by Erhard and Regnier was to import these kind of techniques from analysis to the theory of programming language. The idea is that we know how to compute the derivative of a program. The derivative of a program is just a linear application of lambda x m to n, which means that this is going to reduce to lambda x, where you substitute linearly only once n for x in m. And so if we know how to do the derivative, then we can also do the Taylor expansion. So rather than computing all finite approximants of a program as Böhm tree approximants, we can compute the Taylor expansion of a lambda term. And this will give another kind of finite approximants. So the ambitious goal is to replace the theory of program approximation based on Scott continuity and Böhm trees with this theory of program approximation based on Taylor expansion. And the resource calculus that I just introduced, it's the target language of this operation, Taylor expansion. So Taylor expansion, of a lambda term, gives a power series of resource approximants. So the idea is that the Taylor expansion of x is just x. Taylor expansion of lambda x dot m is lambda x dot t of m. The interesting case is the application, because m applied to n in lambda calculus means you have this application, m a priori can erase or duplicate n or copy it a certain amount of time, but a priori you don't know how many times. So we need to consider them all. So here on the right-hand side, we put a bag with k times the elements that we find in the Taylor expansion of n. We cannot decide k a priori, so we consider an infinite sum over all possible k's. And then since this is a multiset, you are counting too many things, so you need to divide by k factorial. And then for the application that I'm going to show today, and just to bother Lionel a little bit, we're going to consider an idempotent sum, which means that this power series is actually a set of resource approximants. So basically, the Taylor expansion of m applied to n is the set of all resource terms of the form t applied to a bag S1 as k, where t belongs to the Taylor expansion of m, and S1 as k belong to the Taylor expansion of n. And I don't know how many times t is going to use its argument, so I consider all possible choices. Okay, so for instance, the Taylor expansion of omega is non-empty. While the Böhm tree is empty, it is non-empty. It has the same shape as omega, more or less, but lambda x dot x applied to x become x applied to a bag of how many times x here? We don't know, so we consider all possible n. And then it's applied to another delta, so you get another bag here, and you don't know how many times you put lambda x dot xx inside, and you keep going. So Taylor expansion is a static operation, which means that the terms that you're gonna, the resource terms that you're going to find in the Taylor expansion of a lambda term, morally, or at least until a certain point, will have the same structure as the term itself. So if something belongs to the Taylor expansion of a lambda struction, well, it will have the same shape as a lambda struction. If it is an application, it will have the shape of an application. If it is a radix, it will have the shape of a radix. And then one can compute the normal form of the whole Taylor expansion. How do you do that? Well, you know that each term here is strongly normalizable. It means that it's going to reduce to a finite sum of terms. As we don't care about coefficients today, the sum is just a finite set of terms. So I can get the union of all these normal forms. And this will give the normal form of the Taylor expansion of a lambda term. So the point is that each element in the set might terminate in an increasing amount of steps. So you don't really want to define a writing system on the whole infinite set. You can just pointwisely normalize each element and take the union. So now you can prove that the normal form of the Taylor expansion of omega is empty. How do you do that? Well, you take a generic term, you try to reduce, and you see that you will always find a mismatch between the amount of copies that you decided and the amount of copies that are needed. More generally, we'll prove it later if I have time, we'll see that all unsolvable terms have a Taylor expansion which becomes empty once you normalize it. Now, what if I ask you, what is the normal form of the Taylor expansion of y? You say, well, give me y. So this is the shape of y. Nice. So, of course, you can do it, but with a lot of struggle, and it's difficult to find the law that is behind this thing. What we know how to do is to compute the Böhm tree of y. Böhm tree of y, we did it 100 times this morning, is that one. So now, what if I define you the Taylor expansion of the Böhm tree of y, or in general of a Böhm tree? Well, we have seen that speaking of a Böhm tree or the corresponding set of finite approximant is the same thing. So it is sufficient that I define you the Taylor expansion of an approximant A, which will be the very same thing as before, except that I need to introduce an extra case. Taylor expansion of bottom is the empty set. And now I can simply define the Taylor expansion of a Böhm tree of M as the union of the Taylor expansion of its finite approximant. And what Régnier and Régnier proved is that the normal form of the Taylor expansion of M is equal to the Taylor expansion of the Böhm tree of M. And now we can easily compute the Taylor expansion of the Böhm tree of y, because we just apply the Taylor expansion to each finite approximants of y. As a corollary, as a direct corollary, we get that if M is unsolvable, then the normal form of its Taylor expansion is empty, and vice versa. Why? Because it is unsolvable if only if the Böhm tree is bottom, if and only if its Taylor expansion is empty. And so, as another corollary, studying the equality between Böhm trees is the same thing as studying the equality of the normal form of the Taylor expansion. So now we have two ways of approximating lambda term. Either you do the Taylor expansion and then you normalize it, or you compute the Böhm tree and then the Taylor expansion. And the advantage of this approach based on Taylor expansion is that now approximants are closed under application. You remember, you don't know what the Böhm tree of M applied to N is, but you do know what the Taylor expansion of M applied to N is, because it's the same structure. And we have a system which is strongly normalizable, linear, and generalizable, and this approach is easier to generalize to other languages. Of course, there is also a disadvantage, which is that due to the linearization, you will have a lot of indices appearing in proofs, and one needs to be a little careful about it. But to make a omelette, you'll need to break some eggs. So what I did with Barbarossa was trying to apply these techniques to find new proofs of well-established results in lambda calculus. So for instance, we have seen that Scott's continuity is proved by a topological argument, and it entails the contextuality of Böhm trees and the genericity lemma. And we have shown that, in fact, these two results also follow in a more, in an easier way from the commutation theorem by Erard and Regnier. And this was kind of expected in the sense that in the community, in the folklore was, well, this commutation theorem is morally equivalent to Scott continuity. What was more interesting is that Scott continuity itself follows from this commutation theorem. And also other results like the non-existence of parallel law that were usually proved by sequentiality and stability could be reproved using this theorem. Okay, so I don't have much time, but I want to show just a couple of proofs to try to convince you that the new technique is much easier to manipulate. So let's go back to the contextuality of Böhm trees. We want to prove that if M and N prime have the same Böhm tree, then M applied to N has the same Böhm tree as M applied to M prime. So in fact, this follows if I can prove the same thing with the small that substitute equal, because then equal is true if and only if A is smaller than B and B is smaller than A. And by corollary 2, this is equivalent to the inclusion on the normal form of the Taylor expansion of terms. So in fact, this is equivalent to say, let's assume that the normal form of the Taylor expansion of N is included in the normal form of the Taylor expansion of N prime. We have to prove that the same holds for M applied to N and M applied to N prime. How do we do that? Well, let's start by taking a t in the normal form of the Taylor expansion of m applied to n. What does it mean that t is in the normal form of the Taylor expansion? It means that there exists a t prime in the Taylor expansion of m applied to n, such that this t prime generates the t, which means that this t prime is going to reduce to t plus things. But since this t prime is in the Taylor expansion of m applied to n, it must have the same shape, an application. So it has the shape S1 applied to a bag of U1 UK, where S1 is in Tm, U1 UK is in T of n, Taylor expansion of n. But now I can use strong normalization. I can first compute the normal form of the S1 and of the U1 UK, and know that the normal form of S1 is in the normal form of the Taylor of m, and the other ones are in the normal form of the Taylor of n. And by confluence, I can first normalize each component, and then go back to the final result. But by hypothesis, we knew that the Taylor expansion of n is included in the Taylor expansion of n prime. So in fact, the normal form of U1 UK belongs also to the normal form of the Taylor expansion of n prime. And then we simply conclude that they come from a t in the normal form of the Taylor expansion of m applied to n prime. So maybe not very readable, but we only used confluence and strong normalization. Okay, I have 10 minutes. Okay, and then there are some resource approximants that are really like the Böhm's one, in the sense that you can restrict to terms that have as bag either the singleton bag or the empty bag. And basically, the empty bag represents the bottom of your approximant, and the singleton bag is just the application. So you don't need to copy your t many times. So this, I call them affined resource approximants. So linear if they have all the bags in T have cardinality 1. Affine if every bag has cardinality at most 1. And then one can translate the Böhm tree approximant into affine approximants and vice versa. And you can prove that if something is beta normalizable, then its normal form of the Taylor expansion will have a linearized T. And it's an if and only if. So M is beta normalizable if and only if there exists a normal approximant of the Taylor expansion which is linear. You never use the bottom, basically. So this is easy to see. And then with just this property, this additional property, we can reprove the genericity lemma. So we did see the topological proof. So I recall you the statement of the genericity lemma. You have an unsolvable M. You put it in a context. If this reduces to a beta normal form, then for all n, C of n is equal to the same beta normal form. How do you prove this? Well, since C of m is beta normalizable, there exists a linearized T in the in the normal form of its Taylor expansion. So the fact that T is in the normal form of the Taylor expansion means there exists a T prime in the Taylor expansion of C of M that generates the T. As before, this T prime will have the same shape as C of M. So the C comes from the Taylor expansion of the context, and this S1 SK come from the Taylor expansion of M. So we can, as above, first normalize the S1 SK, and then use confluence to come back here. But now we have seen that the normal form of the Taylor expansion of an unsolvable is empty. So when I normalize this S1 SK, since they come from M which is unsolvable, their normal form is 0. So how can it be possible that a context with a 0 inside reduces to something which is not 0? This is impossible, because if a 0 is generated, it annihilates all the term. So in fact, the only possibility is that the whole here did not occur in C in the first place. So you're not substituting 0 somewhere. So in fact, whatever you put in the whole is not going to affect the output, because the whole is not there. And moreover, since the T is linearized, you get that you can reconstruct the shape of T from, the shape of C of N from the shape of T. So it must be the same normal form. Not only it has a normal form, but it must be the same. Okay, so I don't really have time.
If you want questions.
Yeah. So just I say, so the point is that with Böhm trees, you can have a context that does not use its argument for 3 reasons: because it is actually erased, or because it's hidden behind an unsolvable, or because it's pushed to infinity. While here, you have you cannot erase, you cannot have unsolvables, and you cannot put anything to infinity, so you only get the trivial reason, which is the whole is not there in the first place. So this simplifies the proofs. Okay, so I hope that I gave a tour of this big picture, and that now you understand a little better. The only thing I want to say is that I didn't have time to speak about extensionality, but observational equivalences in lambda calculus are usually captured by equality on Böhm trees plus some notion of extensionality. And extensionality is difficult to characterize with Taylor expansion, but recently Blondeau, Patissé, Claire Rambaud, and Vol-Auclair found a way to define an extensional Taylor expansion, which, however, only capture one of the many notions of extensionality that come with Böhm tree. And then one can modify Böhm trees by modifying the notion of unsolvable that you want to consider. So what kind of terms are associated with the bottom? And so I just want to mention that Arial, Kesner, and Guerrieri recently defined a magnificent Böhm approximant. And Victor is going to give a talk on this next Thursdays at the Chocolat meeting. And then there have been the call-by-value version of Böhm trees and Taylor expansion, and also recent research about infinitary linear logic that can be seen as a way of approximating this infinitary lambda calculi. And Serda, Vauclair defined a Taylor expansion for the infinite lambda calculus. So this is not a non-comprehensive list of very recent results that concern this kind of big picture. Thank you very much.
So thank you, Giulio, for this talk. We have some time for questions. Thank you. Any question in the room?
Would you like to comment a little bit about call by value, and in particular if you can use your tools to show again genericity for call by value by means of your tools?
Yeah, indeed. My tools come from call by value in the sense that in collaboration with Pagani and Karinek, we were studying what is a call by value Böhm tree, right? And the point is that we needed to prove contextuality, and we didn't have the whole theory of Scott continuity to redo the proof. And it was summer, it was hot, we didn't want to reprove the whole continuity in call by value. So what I discovered is that at the time it looked like a trick. Hey, look, if we just look at the normal form of the Taylor expansion, it works. And then we tried with genericity, and it does work. So, in fact, yeah, what's good with this approach is that it scales well, at least to those kind of calculi where it is well understood how the intuitionistic arrow translates in linear logic. Then if you get more difficult things, then maybe it does not work for call by need or similar, but if there is a sound logical background behind, usually it passes through.
I wanted just to ask to add something about this call by value issue. Actually, with the Taylor expansion, like you can adapt it to the call by value, as Giulio said, it comes from there. And you can also prove, for example, the stability property that Giulio is one of those that he showed. And this one scales like immediately to the call by value case. Yeah.
Is it in your thesis?
Yes. It will be also, maybe. No, okay, I mean, nothing. I will just also try to. What? I will send it to TLLA. So.
Okay. Any other question or remark? Yeah.
Is there any interest to you to work in a case where you don't have idempotent addition and where you do have coefficients in your Taylor expansion?
So the point is, you can add coefficient, but then you want to prove properties that do speak about these coefficients, right? And what we were trying to show is that you can apply efficiently these techniques even when you're proving qualitative properties of programs. So our idea was to say to the community, if you have a qualitative property, don't think that because it is qualitative, you shouldn't apply these techniques. So the question is, you can add coefficients, but then, of course, you need to characterize properties that do take these coefficients into account. I don't know if I answer.
Ok.
Ariel.
C'est bien ces Parisiens qui attendent de venir à Marseille pour se parler.
So thank you for the talk. I feel like all this works, something hidden behind it is that meaningfulness corresponds to a weak form of normalization. But in some calculi, it's not true. For example, in the lambda calculus with pairs. So do you think this technique will apply then? Because we're losing the correspondence.
I don't know.
Thank you.
I should think about it.
No other questions? Nope. Maybe a point on attribution, I guess. The resource calculus, the one you used, was actually introduced by Thomas and Laurent.
Yeah, with a
because-
different syntax.
Yeah.
A slightly different syntax.
I guess the novelty in Pagani and Tranquilli
No,
was that
that-
they had the promotion.
Okay, this was part of a 3 hours talk that I cut. So in fact,
to make sure.
the paper that I mentioned is about the full resource calculus, and I just presented its promotion-free fragment today.
Okay.
But you are 100% right.
There is a paper by Paolo Tranquilli who perfectly shows that the resource calculus is better. There is a better correspondence between the resource calculus and the proof nets, so proof net representation.
Yeah, we know.
Well, we can discuss this anytime. I'm sorry.
No,
Maybe it is time that we thank the speaker again.
Thank you for your attention.